We already discussed uniform circular motion in kinematics. Now we study the forces acting on bodies during their motion along a circular path. In order to examine any kind of motion in dynamics, we always choose an inertial frame of reference where the laws of motion are valid. If the experiments studying uniform circular motion of bodies are performed in a laboratory, then we can consider this laboratory as an inertial frame of reference with respect to which the motion is described. Let us consider a point mass m moving along a circle with the radius r at a constant speed v. The trajectory of the point-like body is a circle with respect to the inertial frame, where the center O of the circle can be chosen as the reference point. Then the position vector r of the body points from the center O of its circular path to its instantaneous position p, and the velocity v of the body is a tangent to the path at the point p with a constant magnitude. In kinematics, we demonstrated that the angular velocity omega of the point mass rotating around the center O is given by the ratio of the speed v to the radius r. We also saw that the acceleration of a body performing uniform circular motion is equal to minus the square of its angular velocity omega, times its position vector r. This means that the centripetal acceleration of the body always points in the direction of the center O. Since the second law of motion states that the force F acting on a body is equal to the mass m of the body times its acceleration a, the force related to the centripetal acceleration, known as the centripetal force exerted on the point mass, is given by minus the mass m times the square of the angular velocity omega, times the position vector r. By expressing the angular velocity in terms of the speed of the body, the force F can also be written as minus the mass m times the ratio the square of the speed v to the radius r, times the position vector r divided by its length. The centripetal force is the net force acting on a body moving along a circle at a constant speed. Both expressions describing the force F show that it has a constant magnitude but always points in the direction of the center of the motion. Therefore, it is always perpendicular to the velocity v of the moving body. Due to this fact, the velocity is the tangent to the circle in every point along the path of the motion while its magnitude remains constant. The frequency nu and the period t introduced for periodic motions are given by the angular frequency omega divided by 2 pi, and 1 over nu, respectively. We can express the force exerted on a body in uniform circular motion in terms of these quantities as well. Since the magnitude of the centripetal force acting on the body is equal to its mass m times the ratio of the square of its speed v to the radius r of its circular path, it can be written as the mass m times the speed v times the angular frequency omega. If we express the speed as the radius times the angular frequency and substitute it into the right-hand side, then we see that the magnitude of the force is equal to m times omega squared times r. This result can already be written in terms of the frequency or the period, that is we have 4 pi squared times the mass m times the square of the frequency nu times the radius r, or the mass m times the ratio of 4 pi squared to the square of the period t times the radius r. Therefore the centripetal force is inversely proportional to the radius of the circular path for a given speed of the point mass, and directly proportional to the radius for a given angular velocity, or equivalently for a given frequency or a given period of the motion. Here we present some simple examples to illustrate the centripetal forces produced in uniform circular motion. In the first example, we describe an experiment with a bicycle tire leaning on the floor. If we insert a small ball in the tire, then the body can roll along its internal surface. By pushing the ball along the surface, we can set it motion such that it rolls along a circle inside the tire. We can assume that the friction between the rolling ball and the tire is small enough that the ball approximated as a point mass could perform a uniform circular motion, at least for a short time. In other words, the magnitude of its velocity v is constant, whereas it always points in the direction of the tangent to the circular path at its instantaneous position. As a result, the ball has a centripetal acceleration a, since the centripetal force F is exerted on the moving body by the inner surface of the tire. At the same time, the ball also exerts the force minus F on the tire. We can remove some part of the tire and repeat the experiment. When the ball reaches the missing part of the tire, no centripetal force is exerted on it, and the net force acting on the body vanishes. Therefore its acceleration also vanishes, and the ball will perform a uniform linear motion in the direction of the tangent to the circle at the point where it reached the missing part. A similar effect can be seen in the case of the sparks emitted from a grinding stone. Once the sparks are produced, no external force acts on them and they keep their initial velocity. As a result, the direction of their motion cannot change and they follow paths tangential to the rotating stone. In the next example, a ball with a mass m is attached to a string and whirled in a circle by hand. While the ball is in motion, we can feel the centripetal force F pulling our hand, which points in the direction of the center of the circle. By keeping the end of the string in the same position, we apply the opposite of this force on the ball so that it could be held on its circular path. If we cut the string and the centripetal force ceases to act on the ball, then it moves in the direction tangential to the circle at its instantaneous position. In other words, the ball follows the direction of its instantaneous velocity at that point. The tension in the string is due to the centripetal force and its opposite force. If Fmax denotes the force at which the string breaks, then the second law of motion states that the magnitude of Fmax is equal to the mass m of the ball times the magnitude of its centripetal acceleration corresponding to this force. Here the centripetal acceleration is given by 4 pi squared, times the square of the maximum frequency of the rotation of the ball denoted by nu max, times the radius r of the circular path. Then we can express the maximum frequency of the rotation as 1 over 2 pi, times the square root of the ratio of the maximum force to the mass m times the radius r. The third example is the Moon orbiting the Earth, where the centripetal force acting on the Moon is equal to the gravitational force exerted on it by the Earth. The fourth law of motion, that is the law of action and reaction, states that if the centripetal force F is the action, then there is a reaction, that is an opposite force minus F to the centripetal force. This opposite force points outward along the radius of the circular orbit of the Moon, and its magnitude is given by the mass m of the Moon, times the square of its angular velocity omega, times the position vector r of the Moon with the tail at the center of the Earth. However, this force is exerted not on the Moon but on the Earth, which, in turn, exerts the centripetal force on the Moon. This is the case in the first and the second examples as well, where the opposite force minus F acts on the bicycle tire or our hand, respectively. The opposite force to the centripetal force is also known as centrifugal force, but this term has other meanings in dynamics, and we only will use it when we study motion in a rotating frame of reference instead of a rest frame. In another example, we study the centripetal force produced in the motion of a conical pendulum. Such an apparatus is a simple pendulum, that is a point mass m suspended on a string with the length L, where the mass of the string can be neglected. However, in the case of a conical pendulum, the point mass moves along a horizontal circle with the radius r at a constant angular velocity omega, instead of moving in a vertical plane. As a result, the string used for the suspension moves along the curved surface of a cone with the base determined by the circle and with the vertex at the point of suspension. Then the radius r of the circular path is given by the length L times sine phi, where phi is the opening angle of the cone divided by 2. The gravitational force g acting on the point mass is equal to the mass m times the gravitational acceleration g, which is an unconstrained force. The constrained force F' is exerted on the point mass by the string, which is opposite to the component of the weight g parallel with the string. Then the net force F acting on the body, that is the vector sum of the weight g and the force F' points in the direction of the center O of the circular path of the body. The fundamental equation of dynamics states that the mass m of the body times its centripetal acceleration a is equal to the net force F acting on it. Then we can state that the mass m times the magnitude of the centripetal acceleration given by omega squared times the radius r of the circle is equal to the magnitude of the centripetal force F. Since we can obtain the magnitude of the force F from the trigonometric relation between F and the weight g, we write that the mass m times omega squared times the length L times sine phi is equal to the mass m times the magnitude of the gravitational acceleration g, times the tangent of the angle phi. If phi is not equal to 0, we can express cosine phi as the ratio of the magnitude of the gravitational acceleration g to the length L times the square of the angular velocity omega, or as the magnitude of the gravitational acceleration g divided by 4 pi squared times the length L times the square of the frequency nu. This formula shows that we can widen the opening angle of the conical surface swept out by the string, if we increase the angular velocity or the frequency of the circular motion of the body suspended from the string. The operation of a centrifugal or flyball governor is based on this effect. Such a device controls the speed of a steam engine by regulating the flow of the working substance through a throttle valve. As a result, the governor is able to maintain a near constant speed or rotational frequency within reasonably close limits regardless of the load. A typical governor consists of a pair of balls attached to a vertical spindle driven by the prime mover, where the weight g of the balls and the opposite force to its component in the direction parallel with the arms gives the centripetal force F. This force is used as a controlling force which keeps the balls rotating along a given circular path. With a decreasing load on the engine, the speed of the prime mover increases and the central spindle of the governor rotates at a faster rate. Then the controlling force is overcome and the balls move outward. The sleeve attached to the balls by linked arms will slide up the vertical spindle and reduce the aperture of the throttle valve. As a result, the rate of steam admitted to the engine is reduced, which also reduces the rotation speed of the spindle. An increase in the load will have the opposite effect, that is, the balls of the governor rotating at slower rate move downward as the controlling force is weakened. Then the sleeve will slide down the spindle and increase the aperture of the throttle valve. In the last example, we describe an experiment for the study of centripetal force versus the elastic force. The apparatus used in the experiment consists of a ball with a mass m which can move along a horizontal rod. The rod is mounted on the top of a vertical spindle with a spring coiled around it. The ball is attached to the spring with a string over a pulley, as seen in the figure. We choose the length of the string connecting the ball to the spring such that the ball is at the spindle when the apparatus is at rest. If the spindle is rotated, then the ball performs a uniform circular motion with the angular velocity omega. At the same time, it moves radially outward from the center of the motion covering the distance r. In other words, the ball moves along a circle with the radius r. Since the ball is connected to the spring, it will stretch the spring by exerting the force F on it, and as a reaction, the spring exerts the force F' on the ball. Hooke's law states that the magnitude of the elastic force produced by the spring is equal to the spring constant K times the displacement r of the spring. The condition of the uniform circular motion of the ball is that the magnitude of the centripetal force acting on it must be equal to the magnitude of the elastic force produced by the spring. That is, the mass m times the square of the angular velocity omega of the ball times the radius r is equal to the spring constant K times the displacement r. Then we can express the angular velocity omega from this equation as the square root of the ratio of the spring constant K to the mass m. This result shows that there is only one critical angular velocity or rotational frequency at which the ball can perform a uniform circular motion. Since this expression does not depend on the radius r of the circle, the ball can be at any position on the rod during its circular motion. If we modify the radius of the given critical angular velocity, then we will see that the ball will still perform a circular motion for an arbitrary radius. However, by changing the angular frequency, the ball starts to move along the rotating vertical rod. When we studied the motion of a point-like body along arbitrary curves, we described its kinematic quantities in a Serret Frenet frame attached to the moving body. The curve describing the trajectory of the point-like body or the point mass m is given by the position vector r of the point mass with respect to any reference point, and it is a function of time or the arc length s measuring the distance covered by the body along the curve. The moving frame consists of the tangent t to the path of the point mass at its instantaneous position, the normal vector n pointing from the same position in the direction of the center of the osculating circle with the curvature radius rc, and the binormal vector be given by the cross product of the tangent t and the normal n. We demonstrated that the acceleration a of the body can be expressed as a linear combination of the tangent t and the normal n, that is, it can be decomposed in the tangential and the normal directions. The tangential component of the acceleration is directly proportional to the derivative of the speed v of the body with respect to the time, whereas its normal component, that is the centripetal acceleration of the body, is directly proportional to the ratio of the square of the speed v to the curvature radius rc. If we apply the fundamental equation of dynamics stating that the net force F acting on a body is equal to the mass m of the body times its acceleration a, we can write the net force F as the vector sum of its tangential and normal components. We call these components tangential force and centripetal force, respectively. The tangential force acting on the body is given by the mass m of the body times the tangential component of the acceleration a, which is equal to the mass m times the derivative of the speed v with respect to the time, times the tangent t. Since the derivative of the arc length with respect to the time is equal to the speed, we can write that the tangential force is given by the mass m times the second order derivative of the arc length s with respect to the time, times the tangent t. Similarly, the centripetal force acting on the body is given by the mass m of the body times the centripetal acceleration, which is equal to the mass m times the ratio of the square of the velocity v to the curvature radius rc, times the normal n. If the body moves along a line, then the curvature radius rc of the osculating circle is infinity along the linear path of the body. As a result, the normal component of the force, or the centripetal force acting on the body, vanishes, and only the tangential force will accelerate the body along the line. In the case of uniform motion, where the speed of the body is constant, the tangential component of the force acting on the body vanishes, and only the centripetal force will accelerate the body, keeping it on a circular trajectory. In the example of a ball rolling in a bicycle tire, we neglected the friction between the ball and the tire. However, if the ball is set in motion along the internal surface of the tire, then the magnitude of its velocity is reduced by the frictional force pointing in the tangential direction of the motion, whereas the centripetal force is exerted on the ball by the surface of the tire. When we whirl a ball attached to a string, we can perform the experiment by circling our hand. Then the net force F acting on the ball is given by the vector sum of the centripetal force and the tangential force exerted on the body by the string. We denote the tangential force by the subscript 1, indicating that the net tangential force acting on the body can be different. If we does not neglect the frictional force denoted by the subscript 2 exerted on the moving ball in the air, we can write the net tangential force as the vector sum of the tangential force exerted on the body by the string and the frictional force pointing in the opposite direction. If the net tangential force vanishes, then the ball will perform a uniform circular motion. This example also demonstrates that the tangential and centripetal forces belong to the already known types of forces, such as the gravitational, elastic and muscular forces, and do not represent a new type of force. However, the tangential force is an unconstrained force, while the centripetal force can be both an constrained and unconstrained force. In most cases, the centripetal force is a constrained one, as seen in the example. We can also see that these forces do not represent a new type of force because the component equations of the net force F exerted on a body moving along a curve do not describe a law of force. They are just special forms of the fundamental equation of dynamics. If the motion of the body is known, that is, the kinematic quantities describing its motion are given, then the tangential and centripetal forces acting on the body can be determined from these expressions. If our goal is to determine the trajectory, the velocity and the acceleration of the body as a function of time, then these expressions, which are the differential equations of the kinematic quantities, can be solved for these variables. We can also decompose the net force F exerted on the body in the moving frame. Then the components of the fundamental equation of dynamics in the Frenet-Serret frame attached to the moving body are its equations of motion, which are the following. The tangential component states that the mass m of the body times the second-order derivative of the arc length s covered by the body with respect to the time is equal to the tangential component of the force acting on the body. The normal component states that the mass m times the square of the velocity v divided by the curvature radius rc is equal to the magnitude of the centripetal force acting on the body. Since the binormal component of the acceleration vanishes, the binormal component of the force F acting on the body vanishes as well. We can also express the net force F as the sum of the unconstrained force F0 and the constrained force F'. If we decompose both the unconstrained force and the constrained force exerted on the body in the moving frame, then we can express the force terms in the equations of motion as follows. The normal and binormal components of the force F generally consist of the components of both the unconstrained force F0 and the constrained force F' acting on the body, while the tangential component of the constrained force normally vanishes and does not have a contribution to the tangential component of the force F, as we mentioned earlier. The unconstrained force F0 is known, that is, its components in the moving frame are given as functions of time, whereas the non-vanishing components of the constrained force F' are unknown. The arc length s covered by the moving body along its trajectory can be obtained by solving the tangential component of the equations of motion. If we know the trajectory of the moving body, then we can determine all the kinematic variables describing its motion. By substituting them into the normal component of the equations of motion, we will be able to solve them for the corresponding components of the constrained force F' in the moving frame. That is, we can determine the constrained force F' as a function of time.